same structure and hybrid structure of pi sigma वैकेंट ऑर्बिटल रेजोनेंस सिस्टम। ठीक है, इसमें एक सल्फेट आयन का इज इम्पोर्टेंट जो कि आपको नोट करना है। ठीक है, प्लीज डू दैट। सल्फेट आयन, this is sulfate ion. Sulfur has vacant d orbital. The two side oxygen atoms have extra lone pair of electrons due to their negative charge, and because of this these lone pair of electrons can go into delocalization in that vacant d orbital. एक आएगा तो दूसरा ओपन होएगा, therefore this kind of system is being formed. फिर ये अंदर आएगा, ये ऑर्बिटल में d ऑर्बिटल में delocalize होगा तो this will get free. further ये ओपन होएगा, ये आ रहा है, फिर so sequence में this is coming into participation, this is getting freed up, फिर this is coming into participation, this is getting freed up, creating a new all the time creating a new structure. So in total there are going to be 6 canonical structures altogether. This is the first one, this is the second one, then the third one, then the fourth one, then the fifth one, and this is the final 6th. So altogether there are going to be 6 canonical structures, and final resonance hybrid is going to look something like this. ठीक है, तो हाँ टर्न बाई टर्न शिफ्ट होते जाएंगे डबल बॉन्ड, एंड इन एनी pair of sulfur oxygen atom there are going to be 2 plus 1 plus 2, 5 plus 2, 7 plus 1 plus 1, that is 9. Total 9 bonds, and there are 6 structures. Therefore, the bond order is going to be approximately 1.5. All the bond order is going to be 1.5, and all the oxygen atom is going to have a partial charge of, partial negative charge. That is, negative charge is being delocalized over all the centers. Is that okay? So kindly draw it.
So the bond order basically helps in predicting
bond length, bond strength.
बॉन्ड स्ट्रेंथ से वो इन्वर्सली होता है,
बॉन्ड स्ट्रेंथ से वो डायरेक्टली प्रोपोर्शनल होता है और बॉन्ड लेंथ से इनवर्सली प्रोपोर्शनल होता है। the thing is like that. SO4 2 minus का हमने लिया, ठीक है. Let us try to draw the resonance structure of H2SO4, ठीक है. H2SO4 का हम लोग करते हैं. So what we find is there are just 5 resonating structures. एक कम हो जाता है. And the bond order is not exactly same everywhere. ठीक है. जहाँ पे डबल बॉन्डेड सिस्टम होता है, ऑक्सीजन हाइड्रोजन नहीं बॉन्डेड होता है, वहाँ पर बॉन्ड ऑर्डर हैपेंस टू बी 1.6, whereas बाकी दो प्लेसेस पर it happens to be 1.4. ठीक है. Now this disparity in bond order is obviously going to impact the bond strength, impact also the electronegativity of atom, the concerned atom, and therefore it is going to modify the character of the molecule. ठीक है. This system is going to be potentially less stable, because lesser amount of delocalization is taking place compared to this one, where greater deal of resonance is taking place. Now this is something which helps in movement or increasing the acidity of H2SO4 from normal level to a very good level. ठीक है. Or that is one of the key reason which makes this particular acid a very good acid or very strong acid. हाँ, this one is relatively potentially unstable compared to this one. ठीक है. यहाँ पर रेजोनेंस स्टेबलाइजेशन कम है, यहाँ पे बहुत ज़्यादा है. द गैप इंक्रीजेस. इस स्ट्रक्चर से इस स्ट्रक्चर में जब हम आते हैं ना, द गैप इंक्रीजेस एंड देयरफॉर हेलो. The second pattern which allows the resonance to take place is pi, sigma and negative charge or lone pair system. Pi, sigma, negative charge or lone pair system. This is high energy system. This is relatively low. So this high energy electrons try to delocalize in pi orbitals. How it happens? I have taken a very simple case of CH2NH, CH2 double bond CH and NH, or CH2 double bond or CH and OH. These two systems. ठीक है. इसमें like this is double bond. The double bond is partially sitting on one of the orbital. This is being created as the second orbital. The bond pair, the lone pair of nitrogen is then coming into this to form a double bond, creating a negative charge over here and a positive charge on this nitrogen. सो इन दोनों का ये हमारा पैटर्न होगा, एक रेजोनेटिंग स्ट्रक्चर, दूसरा रेजोनेटिंग स्ट्रक्चर, कैनोनिकल या रेजोनेटिंग स्ट्रक्चर, and then then we will have a hybrid structure which could be given like this. Okay, or I can plot it in a better way. Finally, hybrid structure as CH2, single bond CH, single bond. M पे positive charge आएगा, delta positive, and carbon पे delta negative. Final hybrid structure में, और यहाँ पर obviously यहाँ पर भी आएगा. This is going to be first canonical structure. The other canonical structure would be CH2 minus single CH, single O, two lone pair of electrons, a double bond, and the hybrid structure is going to look like CH2 single bond, CH single bond, O, two lone pairs, delta negative and delta negative. This will be the hybrid structure. नहीं तो यहाँ पे प्लस नहीं आएगा, यहाँ पे माइनस चार्ज पहले से था ना. That went to this, the extra negative charge, or extra, the charge was because of extra electrons. Now that has got delocalized, so the charge will simply disappear or vanish. No positive charge will come. Positive charge can come only if the delocalization is taking, or number of electrons are getting delocalized from a neutral atom. Neutral atom से जब हो जाएगा तो negative efficiency आएगी, which is represented as plus charge. Negatively charged system से अगर delocalization हो रहा है, it is not going to be indicated as this thing, positive charge. That will simply nullification of the negative charge. So draw it again, the middle of the board. CH2, double bond, CH and OH. Two lone pair of electrons. I. This is CH, and OH. One lone pair will remain, other will get delocalized. This will be delocalized like this. This will come here, this will come here, this will come on carbon atom. The double bond, the pi electron will come on carbon atom, creating a negative charge on carbon and a positive charge on oxygen. There will be a double bond. Therefore, resonance hybrid will be something like this: CH2, CH, OH, delta negative and Hello. Apart from that, we can deploy that same thing over this structure. We can delocalize it in, we can delocalize the electrons in this system uh, among these structures to create the resonance hybrid of this sort. Okay. And accordingly we can create the bond orders, और इसमें सारे bonds का strength exactly same नहीं है. That we can ascertain based on the bond order which we are finding. एसिडिक ये नहीं होगा क्योंकि इसकी इलेक्ट्रोनेगेटिविटी बहुत ज़्यादा नहीं है. ठीक है, ऑक्सीजन की वहाँ पर इलेक्ट्रोनेगेटिविटी ज़्यादा होना इज अनदर रीजन. ठीक है, और डिलोकलाइजेशन का अनिवार्य होना इज अनदर स्ट्रॉन्ग रीजन. ठीक है, सो काइंडली नोट दिस डाउन. इसका स्ट्रक्चर आप खुद से बनाओ. यही बेस है mainly, and CH2 minus. So you can draw it. बिना देखे ड्रॉ करना है. The third system where delocalization can take place is lone pair sigma vacant orbital, which happens generally in case of H2SO4, H3PO4, HNO3. These acids show lone pair and vacant orbital delocalization. Let us see one by one in detail. The transfer of electronic charges at the bonded pair of electrons in H3PO4 has been shown or displayed like this. Oxygen has a double bond and two lone pair of electrons from this first structure, the second canonical structure, and third canonical structure, and fourth canonical structure has been formed. This is the normal or usual representation of H3PO4. From here, the electrons are getting transferred and a double bond being formed, and this side creating a positive charge. Positive charge on this oxygen. Further, when there is when we are going from here to here, there is this lone pair of electron which is getting transferred. Further, there can be transfer of the second the three marked oxygens in one of the case, blue marked oxygen is participating in the delocalization of its electrons, lone pair of electrons. In other case, the green shaded oxygen is participating in the delocalization of electrons, and in third, yellow shaded one is participating in the delocalization of this pipe via the vacant d orbital of at the end creating this hybrid structure. Similarly, HNO3, the normal structure actually looks like these are the normal structure looks like nitrogen, double bonded oxygen, coordinated, and OH. And this can be treated as first canonical structure. there is a negative charge on this and there is a positive charge on this because of this donation. Now this that means this oxygen will have a bonded pair and two lone pairs. One pair of electron can then get delocalized to form a double bond, and this double bond will open up to create this structure. Then this one is being created, and finally the third one is being created when the lone pair of this oxygen atom is participating into the delocalization. Final hybrid structure looks something like this. When these two oxygen having delta negative charge, this oxygen which is bonded with hydrogen ends up having a delta positive charge, and nitrogen also has a develops a delta positive charge in hybrid structure. Okay, how it is forming? Nitrogen is getting double bonded with this oxygen. So two of its valence electron out of total 6 are participating into double bond formation. Nitrogen oxygen forms one single bond, oxygen hydrogen form one single bond. Octet of this oxygen and this nitrogen has been fulfilled with one of its lone pair remaining within itself. Now this lone pair is donated to or coordinated with another oxygen atom, so that octet of this oxygen atom will get completed. After coordination, the structure or the electrons are going to be like this oxygen has not utilized any of its electron in bonding. So all 6 electrons of this oxygen are well placed as a lone pair on this oxygen atom itself. Thereby it develops a negative charge over itself, and nitrogen, due to coordination of its or donation of its lone pair of electrons towards oxygen, it develops a positive charge. This structure is same as this base structure, the first canonical structure. Then the migration of electrons has been shown. The lone pair of one of the lone pair of electrons is then participating in with N to form a double bond. Now this time the pi bond of nitrogen and oxygen is getting opened up to free up an orbital, forming this set of canonical structure, and then the third canonical structure is being formed by participation of electrons from oxygen which is bonded with hydrogen. Thereby creating, and now we can see that all these structures have a positive charge on nitrogen. Therefore, nitrogen will develop a positive charge in hybrid structure, and the oxygen atom will also develop oxygen atom attached with hydrogen will develop a delta positive charge, whereas the other two oxygens will develop a delta negative charge. It's not just vacant orbital, it is also pi orbital. I mean lone pair, sigma, bond and pi orbital overlapping. The third example, HNO3 example, will actually fall under second category, where lone pair is being getting delocalized with pi bond. Nitrogen do not have a vacant d orbital, so this is going to be an example of pi sigma lone pair delocalization. Pi sigma lone pair delocalization. Next one being the next category of delocalization is. We have some more examples of lone pair and backend orbital delocalization that happens or that takes place in case of BCL3 or for that matter BF3 or even BBR3 and BI3. Boron dichloride, tribromide, triiodide and trifluoride. In all of them this type of bonding takes place or this type of delocalization takes place. Boron has a vacant p orbital, boron has a vacant p orbital where chlorine actually donates its lone pair of electrons, and all three chlorines donate in this vacant orbital one by one, creating a hybrid structure like this. So in case of BCl3, it happens to be like BCl3 boron Cl and Cl. These lone pairs are shared with the vacant orbital. They are directly shared with this vacant orbital turn by turn. So one of the structures would be the Cl, double bond B, single bond Cl, single bond Cl with minus charge on B and plus charge on chlorine. Secondly, it is going to be Cl, single bond B negative, Cl, double bond positive, Cl, followed by third canonical structure the fourth canonical structure where third chlorine will delocalize its electron. The hybrid is going to look like boron, Cl, Cl and Cl. The single bond is getting modified. All these borons are having negative charge except this one. So this is going to have a delta negative charge and these all chlorines are going to develop a delta positive charge. This sort of bonding is also known as back bonding. The reason behind it is why we call it back bonding is generally we have transfer of electrons taking place from low electronegative atom to high electronegative atom. But in these cases, generally high electronegative atoms have one or more than one lone pair of electrons which are getting donated towards a vacant orbital, which is reverse to the concept of bonding where electrons are getting in normal concept of bonding, electrons generally migrate towards higher electronegative atom, whereas in this case it is moving, the electron density is moving towards a vacant orbital which is which generally has lower electronegativity, and therefore this sort of bonding is known as back bonding. It is also referred as back bonding. The next set of example can be NCl3. Now in BCl3, there has not been any change of as such of hybridization or any other changes except delocalization. In case of NCl3, the delocalization also brings some change to hybridization of the nitrogen atom, the central nitrogen atom. Nitrogen atom having bonded with 3 chlorine has a lone pair which gets delocalized to the vacuum d orbital of chlorine. Now this one is not an example, this one is this cannot be considered as an example of back bonding. However, it is definitely an example of lone pair sigma and vacuum d orbital delocalization. Lone pair sigma and vacuum d orbital delocalization. Vacuum d orbital delocalization, where the vacuum d orbital of chlorine atom is participating into delocalization to accommodate the lone pair of electrons of nitrogen. So what is happening is we are having formation of a double bond of NCl3. This double lone pair of electron is being coordinated to the first Cl, then to the second Cl, and then to the third Cl in sequence, creating a negative charge on chlorine and a positive charge on nitrogen. So this could be first structure, second structure, third structure, and fourth. The sum total of 4 structures is this structure. In which nitrogen develops a delta positive charge and all chlorines develop a delta negative charge. Not only this, the hybridization of nitrogen changes from sp3 in this case, sp3 in this case to sp2 in this case. That becomes a major reason why we never say this structure as a canonical structure. The canonical structure are these structures only. These 3 structures are canonical structure of this nitrogen trichloride molecule. This structure is not considered as a resonance structure of NCl. So over here we have seen that the resonance is also responsible for change of hybridization in certain molecules. Not only this, we have another example where we have pyridine, 4 carbon and 1 nitrogen chain, a total 5 atoms in a ring. This is aromatic system. This happens to be an aromatic system. In general, it appears that nitrogen has formed 3 bonds and it has 1 lone pair of electron. Now this lone pair of electron of nitrogen generally stays in a hybrid orbital. However, in case of pyridine, this lone pair of electron, instead of going to hybridized orbital, it prefers to stay in unhybridized or pure p orbital and thereby participate in process of resonance to provide extra stability. Why I am saying this is, see, hybridization was happening just in order to create some greater space between the orbitals so that the potential energy of the atom or the electrons, the valence electrons, can be minimized. But in this case, if this electron does not go to a hybrid orbital, and supposedly remains in its pure orbital, it has greater opportunity to get delocalized and lose a greater amount of potential energy compared to what it would have lost when it would have participated in hybridization. Therefore, it opts for the second route, that is delocalization through